a general sense, limits allow us to determine what value a function is approaching when we use a particular input. Not necessarily what the function gives us as an output, but rather what value it's getting arbitrarily close to. Let's explain limits using an analogy. Suppose you are watching TV and start getting a massive craving for pizza. Fortunately, you just happen to have some leftover pizza in the kitchen. So you get up from the couch and start heading towards the fridge. In this instance, if someone were to describe where you are going, they would say you are approaching the fridge. They would be confident in their description because as you keep walking, you are getting closer and closer to where the fridge is located. This example is the same thing we want to do with functions. When we take the limit of a function, we are describing where they are going. Let's see an example of this with the function 3x squared minus 1. For this function, I'm really curious what value the function is approaching as I use x values close to the number 2. Let's see this by using some inputs like 1.9, 1.99, and 1.999. When I use these, I get values such as 9.83, 10.8803, and 10.988003. From these values, it appears that the function is approaching 11. So we say that the limit of the function as x approaches 2 is 11. Remember, what I'm really saying here is that we can get arbitrarily close to the number 11. I just have to pick values that are sufficiently close to 2 in order to do it. Now at this point you might be thinking, that's fantastic, but couldn't you have also found the limit simply by plugging 2 into the function? Wouldn't that also give you 11? In this instance, the answer is yes. But the focus with the limit should be on what value it's approaching, and there are some functions where you simply can't plug in a number to find the limit. In other words, they are not always the same. Let's cover this by going back to our pizza analogy. Like before, you've been struck with a craving for pizza. So you are headed towards the fridge for a quick snack. Now, in one scenario, the fridge is there, loaded with pizza, and you can easily satisfy your craving for pepperoni. But in an alternate scenario, the fridge is gone, possibly stolen by pizza-craving ninjas, and you are left empty-handed. Even though both of these situations are completely different, your behavior leading up to them is exactly the same. In either case, you are still approaching the fridge. This is the key difference with limits. They are used to describe what value a function is approaching. They are not used to describe the value the function actually reaches. Let's see how this works with yet another function. Let's go ahead and use x squared minus 4 all divided by x minus 2. Like before, we are interested in what value the function approaches as we use x values close to 2. Let's go ahead and choose some inputs like 1.9, 1.99, and 1.999. When we use these, we get values of 3.9, 3.99, and 3.999. From these, it appears that the function is approaching 4. So again, we say that the limit of the function as x approaches 2 is 4. If you try and find this value by instead plugging in 2, something strange happens. When you plug 2 into the function, you get 0 divided by 0. This shows that the function doesn't actually ever get to 4. In fact, a quick look at the graph shows a hole right where 4 is. Despite the hole, the behavior of the function leading up to it is the same. Since the behavior is the same, we still say that the limit of the function as x approaches 2 is 4, even though it never actually gets there. Hopefully both of these examples really highlight how limits focus on the behavior of a function, what they get arbitrarily close to. One thing we still have left to cover is what it exactly means when we say that a function gets arbitrarily close to a value. But don't worry, we'll be able to tackle that tricky problem in the next video when we introduce epsilon and delta. Thanks for watching.